All right, hello everyone. I know it's an interesting start to 2025. Thank you for joining me today. I'm actually without power again. Last time we were without power for 4 days. We had it for 2 days, and now it's out again for probably another 4 days. But we still have internet, hopefully. So it went out in the middle of last lecture. So we got the generator going, and everything's good. My big monitor is working. So we'll just keep that. We'll hope that continues going. A couple orders of business first. Please go into the clicker, the iClicker thing. I'm going to do this two ways. I'm using the iClicker with no geofencing, but also Zoom also has a roster that shows me who is here and also for how many minutes. So being here for like a minute, 2, 3 minutes is not sufficient to get credit. It needs to be more than that, unless there's some kind of major issue, um, because of what's going on. Then we can work with that. Anyway, so today we're going to talk about a variety of things. We didn't get through all of it. That's okay. We're a little bit behind, which is unfortunate, but it is what it is. So I will give you a few minutes to let me switch over to the slides. This is a new setup for me. I'm using OBS, which lets me switch really easily between my terminal and my slides. And on a big screen, it's so much easier than using Zoom to do this. So we're going to do a lot of walkthroughs and demos today. So yeah, we'll go ahead and get started. If you need to ask any questions, feel free to type them into the chat. If it's not something that is basic, like is more involved, feel free to raise your hand or whatnot, and then I will stop and you can get on your mic and ask whatever you'd like. We want this to try to be interactive. So we won't get to this today, unfortunately. Anyway, so I sent you all an email through Piazza and my UCLA with a series of steps that you should take before the lecture. So right now you should have your EC2 instance started and you should be SSH'd into it. If you haven't, you need to do that like now. You had 3 hours now to do it, and then follow these directions. So you need to install something. It's very quick. You need to download the data. One of the pieces of data, it takes about 10 seconds to download and then about a minute to extract. So I'm going to go ahead and get started. If you haven't done that, please do it. Use the directions that were provided on Piazza so you can copy and paste. I know it's hard to read here. Okay. So today we're going to talk about a couple of things, mainly intro to Unix, how to navigate through a Unix or Linux system. This has always been kind of a challenge, and it's really important to learn this because a lot of corporations still use Windows and whatnot, and the rest use Linux or Unix or something of that nature. So you should know how to work with these different things on that system. We'll also talk about basic data management in the shell. So you don't have to dump a huge file into R and exhaust your memory in order to do basic data analysis or basic data management, I should say. You could do a lot of it on the command line, and that's the purpose of this lecture and half of next week's lecture, is to teach you how to do that and without having to read all the data into RAM. So we do it row wise, and there's a lot of processing that you can do before you put it into R, and it's super helpful. It's a lot of fun, and I think you'll be mind blown about this. It's pretty interesting, in my opinion. So, what is an operating system? So, you've heard the term, I'm sure, and most of you probably know what it is. But an operating system is a piece of system software that basically manages everything running on the computer. It manages hardware via hardware drivers. It manages other software that needs to interact with the hardware and with the operating system. And it provides common services for those applications. Ones you're familiar with are Mac OS, obviously, Microsoft Windows still. Linux is actually not an operating system. I put it up here though because it's close enough to one. Linux distributions are operating systems. We'll talk about that in a moment. And then some of you use Chrome, so Chrome OS is also an operating system. Now, or at least two others for mobile, and that is Android and iOS from Apple for different kinds of mobile devices, iPads, phones, and all that kind of fun stuff. Android is a version or a variant of Linux, and iOS is a version or variant of Mac OS. So Unix was developed in the 1970s, so very, very long time ago, still very relevant, at Bell Labs. So back in the day, Bell Labs did a lot of research on a variety of different things, but their main focus was, Ma Bell and the telephone companies. So Bell Labs was kind of the research arm of telecommunications back in those days. Xerox was another very hot company back then. So now it's like Google and Apple and Netflix. Back then it was Xerox who made copy machines, and Bell Labs, which was telecommunications, and of course NASA and whatnot. Now, it was developed by these guys, Ken Thompson and Dennis Ritchie. These names you will see if you continue working in this area or if you've programmed in C. Kernighan and Ritchie wrote like the Bible for C. I don't know if they were actually developed the language, but you may have heard their names before. Now, Unix is actually a group of systems, not an operating system itself. It's not even really a group of operating systems, to be frank. Um, they're generally based on two older systems. One's called System V, which is from IBM, and the other is called BSD. Most Unix and Linux today is based on BSD or some kind of variant or evolution of BSD. It's mostly free and open source, but there are commercial Unix systems, including Solaris, HP, IRIX, and AIX. I don't know if they still exist anymore. I know that when I was in college, I had no idea what they were. They were like dying out at that point. Open source versions of Unix, though, include FreeBSD, NetBSD, and OpenBSD, as well as Linux. So Linux is an open source variant of Unix. Now, if you use the Mac OS operating system is based on Darwin, which I believe is some variant of what's called MacBSD, which is a variant of BSD. So it's closer to Unix than Linux, actually. And Linux is a Unix-like operating system or series of operating systems. We'll call it series of operating systems that are open source. Linux itself is actually not an operating system technically, and Unix and Linux are not the same thing. So Unix systems are very powerful, but they're designed to be typed. So you type a bunch of commands into an old mainframe at a console that was a big clickety clackety keyboard, and that was it. There was no graphical user interfaces back then. And nowadays, we mostly work with GUIs or graphical user interfaces. So on Mac and on Windows, you double click things, you drag things, you click on the menu, all of that kind of fun stuff. You can't do that on a pure Unix-based system, though in Linux, they have developed some graphical user interfaces to be used similarly. Now, how I was introduced to Unix, I meant to put a screenshot or a video of this, was from a very old movie called Jurassic Park. And I don't know, the dinosaurs are trying to break into this control room or the visitor center, whatever. And the little girl is like trying to save the park or save them from the dinosaurs by hacking into the system and closing all the gates or something like that. And it was this weird system where like you flew around. It was kind of a GUI. It wasn't Unix at all. This is a Unix system. I can do this. That's the first time I had ever heard of Unix, but it doesn't look anything like what they actually portrayed it in the movies. All right, so Linux has a variety of what are called distributions, and each distribution is an operating system. Linux itself is what's called a kernel. It has base code that helps boot a system and helps manage certain parts of the really important parts of the hardware. But the rest of the system is an operating system, requires an operating system. And Linux distributions provide those operating systems. So these three up top here are all what are called Debian-based systems. Debian's fine. I use Ubuntu. Your EC2 instance is Ubuntu. I believe it's still the most popular distribution of Linux. It's easy to use. It's fun to use. Debian is its parent. So Ubuntu is derived from Debian. And this other one, Linux Mint, is like a really small pared down version of Linux. I believe it's based on Debian. What really distinguishes these, there's a lot of distinguishing factors, but to me, it's the package manager, how you install things, pre-made things. So on Mac, you might have Homebrew or Mac ports. So you do brew, install, whatever. And Linux does the same thing, but it depends on the type of system. So in Debian-based systems, they use something called APT or aptitude or aperture, I think is what they sometimes call it. It's very, very easy to use. So in all three of these operating systems, it's easy to install packages by using those commands. There's another set that's based on what's called Red Hat. It's now commercial, but it used to be open source or free. And Red Hat systems include Fedora and CentOS that are still used, but now they're mostly closed source and commercial. And these use a package manager system called Yum. To me, it's not very yummy. I've had a lot of problems using Yum, so I'm more of a Debian guy. There's this other one that computer science people like called Arch Linux, which is a very bare bones Linux distribution that's often used on like Raspberry Pis and whatnot. And their package manager is called Pac-Man, like the video game for package manager. There's this other one called Manjaro, which is a pared down version of something. I don't know what. I haven't used it. It sounds an awful lot like a pharmaceutical that's on TV constantly. So anyway, those are the main types that are popular today. All of them offer a command line interface and a GUI, a graphical user interface. But the GUI is typically not dictated by the distribution. So Mac and Windows have their own GUI that is specific to Mac and Windows. Linux, no matter what distribution you use, you can use typically the same GUIs. So some of them include GNOME. That's the most popular one. And another one is KDE. There's a couple others as well. GNOME is the most popular one. So SUSE, Ubuntu, Debian, Fedora, whatever, you can usually install GNOME on them. Okay. Now, there's some terminology that we need to try to get right here. I use these terms interchangeably. A lot of us do. It's just kind of the way that it goes because nowadays we're not typing at big monolithic terminals, what are called dumb terminals, where you have a keyboard, a monitor, but nothing's actually happening at your workstation. All the data is being sent to some server somewhere else, and all the responses are being sent from the server back to the screen over a network via this dumb terminal. But there was a lot of confusion. There has been a lot of confusion about these terms, so I want to try to um, explain them to you. The first is the concept of a shell, and that's a lot of what we're going to talk about today is the shell. Here it is. It's a program that allows the user to interact with the operating system via the command line, via commands. I'll type just commands for now, although technically it's through the command line. Typically, there are many shells. Typically, all shells have the same basic software or commands. These are sometimes called GNU commands or POSIX commands. So every Linux shell has CD, it has ls, all of that fun stuff. That's standard. But sometimes the options may be different. Sometimes the way the shell behaves might be different. But more or less, the general functionality remains the same. Now, there's a lot of different kinds of shells. Let's see. Terminal. What is a terminal? Sometimes it's called a console, older term. The terminal is an application. It used to be a piece of hardware that is used to connect to some Linux server or to some server and interact via the shell. So you use your terminal application to log into the server, and then it presents you with the shell that's on the server. Some examples of this on Mac, if you're curious, iTerm 2 is a great replacement for the standard terminal that comes with Mac OS. On Linux, there's one called Terminator, and Windows has some as well. Putty is another one that's for Windows. So that's the terminal. The CLI or command line interface is what's required to type in commands. So oftentimes, I have I have a server here, and sometimes I need to figure out how to do something. And the only directions that I can find are for the friggin' point and click interface. So I have to add to my search, I'm looking for the command line interface way to do it. And then typically I can find the commands. The server here, yeah, a server can either be, it could be your local machine. So you open a terminal, which on your local machine, which connects to the shell on your local machine. So on your Mac, on your own local Linux server, or a remote server, like an EC2 instance, or any other type of server. Yes, so it could be either. It could be a local server or a remote server. It's just some server. Okay, so shell is the language. Shells do have a language. They have a syntax. It's not only a language, so it's a syntactic structure, I'm gonna say, rather than a language. So you have you can write shell scripts, which uses a language, but then there's also just different ways of interacting with the computer or with a server based on that shell. So trying to come up if I have a good example. Basically, every shell is going to be programmed differently. If you use Bash versus C shell, the code that you write for the shell script is going to be different, or at least a little bit different. The commands are mostly the same, though sometimes the options and the defaults of those options are different. So I think that's how I would put it. So I wouldn't say it's a language per se, except for if you write a shell script. Now, two more terms. SSH. Sometimes we'll say SSH into the server. Execute this command via SSH. Now, it's wrong to say SSH into your local server. You can do that, it's possible, but you're using the term incorrectly for the most part. SSH is actually a network protocol. It's an internet protocol. That securely connects a user machine to another machine. Your laptop, your server, whatever, to another machine. So a little diagram of this, you have some origin, which is you, basically, and you connect to some server or some other machine, destination. And this channel of communication is encrypted, and it's via a protocol called SSH. There are other protocols like Telnet that used to be very common, but they're very insecure. Um, there's like others like TN3270, which are used on mainframes and whatnot. But that's just the protocol. You can actually download a GitHub repository over SSH. So it's not the same thing as executing commands. It's just a protocol. Finally, we have the command prompt. This is just where you type in commands. At where you type in commands. So versus a GUI. So we don't need to talk about shells, what shell you're using. We typically say you write your command on a command line interface at the command prompt. This guy here, this is the logo for iTerm2. That is the command prompt. Okay. You have two shells here, a turtle shell and a seashell. That's relevant in a moment. Now, yeah, often these terms are used interchangeably, including myself, but they really shouldn't be. There's less of a difference now than there were back in the 70s and 80s. So we're going to focus on interacting with Linux, Ubuntu Linux, in a shell by executing commands on the command line at the command prompt. But not only at the command prompt, we'll also write scripts as well. We may not this quarter because we're a little bit behind. Usually we talk about it. To be honest, it's not the most relevant thing. So we may not. We're going to focus on the bash shell. So a bash is a fancy word for an exclamation point, and it's actually an acronym for the Born Again shell. So Born is a person. He created his own shell called the Born shell. The Born shell is sh, and bash is bash, like bashful. There's also the C shell, which is csh, and tcsh, which used to be the default on Mac OS, and also the Z shell. So modern Macs use zsh or the Z shell as the default on them. So that's people really like ZSH. I haven't used it at all. Maybe someday I will. There's a lot of cool command foo you can do if you understand the command line really well and your shell. I understand the command line well, but not shell programming as much. Now, we have to work with files and directories in Unix and Linux and whatnot and in the shell. And the directory structure is a tree. So you have a root to the tree, and then a bunch of branches and paths through the tree that end at files. So each interior node is a directory. All the leaves are files, or possibly empty directories too. And every route through this tree is called a path from math, and we'll get to that in a moment. But on a Mac or on Windows, if you're using the graphical user interface, you don't really take this into account. You don't really pay attention to what the path is to a file. You just double click through your way. And if you get lost or somewhere in the file system, you click the back button, you click the back button again, and you double click and whatnot. But in the shell, it's different. You have to kind of remember where you are or figure out how to get back to where you want to be using commands. So the root directory is denoted by a slash. All other directories after that are separated by slashes. So for example, the one that you're most familiar with at this point is home slash Ubuntu. Your username on your EC2 instance is Ubuntu, and every user has a home directory. On your 402 on the 402 server, you also had a home directory. This is the root, this is the home directory, and this is your home directory. Now, directories are similar to folders on Windows and Mac, basically. You could say they're analogous. So a path to a file would look like home, Ryan, file.txt, for example. Now, there's several directories that you should be familiar with. Not so much for this class, but for your future. There's user local or USR local bin. This contains programs that you install. So local programs that you install that typically are not installed by a system administrator. So we're going to eventually install Spark, and we're going to install that in a directory called usr/local. And we're going to put the whole Spark package under usr local. Then under Spark, you're going to have a bunch of other directories like etc, bin, and the bin directory will contain the executable that you use to run Spark. Now, in order to find these particular commands, you have a variable called the path, which we'll talk about when we need to talk about it. But the path tells the system where to look for things when you type a command. So when you type Spark after installing it, you're going to get a command not found. You have to tell your shell what the path is, where to search for these different executables. And so we're going to have our path variable will be set to usr/local/spark/bin. Then when you type Spark, it'll load the proper command. User/bin contains executables that the system administrator installs, typically using sudo. So sudo basically turns you into a super user for a short period of time for one command, and then you revert back to your regular user. Then we have /bin. These are intense. These are programs that are installed in the operating system that you should never delete. So the shells, like sh, is installed in /bin. So /bin/bash/bin/sh is stored in /bin. Then you have your home directory, which is very important. Then you have a TMP or temporary directory. This directory is cleared on reboot. Sometimes you can configure it to clear more regularly. But if you have a file that you know you're not going to need again, and you're just doing some intermediate work, you could do it in /TMP, and then it just goes away when you're done with it. Then you have /var, which typically contains logs. As data scientists, you're going to be mining a lot of logs that contain interesting data. They typically originate in the /var directory. Then finally, you have /etc. It's pronounced Etsy, not etc. This is where the startup got its name, ETSY, Etsy, is from nerd culture, etc, the directory. Typically, this is where all of your configuration goes for your system and for packages on the system. Okay. Next, there are two types of paths in the file system, the absolute path and the relative path. Path being path to the tree. Absolute paths are unique. They identify exactly one directory or exactly one file through all of the different components of the path. So if I have this homework file, it is uniquely identified by its path, starting at root down to the leaf. So /home/Ryan/school slash homework.txt. Root to leaf. Now the relative path, absolute paths get annoying very quickly. The relative path is usually what you want to use here. This path is relative to where you currently are in the file system. It's like a pointer. I want to go into that directory, the third directory here. I don't have to give a specific absolute path to get to it. Typically, the relative path is with respect to your home directory, which is where you're dropped when you log into the server, or to your current working directory, which we'll talk about in a moment. Your home directory has a shortcut, which is a tilde, or a twiddle, sometimes it's called. So I can write home Ryan file.txt or tilde slash file.txt. It's just a shorthand, but that is actually not a relative path. Tilde is just a shorthand. Okay. So here, this is optional. So let's say I'm in my home directory. You have a zip file called filesystem.zip. Once you unzip it, you will have these directories in there so you can follow along. If I want to go into the school directory, I don't need to specify the home directory. I'm in the home directory. I just specify that I want to go into the school directory, or that maybe I want to read the homework.txt file that's in the school directory. I specify it relative, school slash homework.txt. This is actually optional, this dot slash. You can just put school slash homework.txt if you prefer. Now, what happens if you get lost in the file system? My cheat sheet's in the wrong order here. It's backwards here. Okay, so I got to go up to this one. All right. So both of these are equivalent. The top one is an absolute path to homework.txt. The second one is actually not a relative path. It uses a shortcut. The relative path would be school slash homework.txt. I don't know if you have this file in there. It's just a sample. And again, you're dropped at the home directory when you first log in. Now, is there anything else I wanted to say here? Because the order here is just so bizarre. This is what a file system tree looks like. To save space here, I don't put the root directory, but the root would be up here. It has, some children. It has the USR directory. It has a temporary directory. It has a bin directory, all kinds of stuff. And then, of course, you have the home directory. Under the home directory, I have a directory for each shell user, Ryan and Sam. We don't care about Sam. Poor Sam. Now we'll just look at Ryan's directory. That's me. I have a school directory and a work directory. And in your example, you also have a photos directory. And in the school directory, I have a homework 1 text file, a notes PDF file, and then under work, I have a homework 2 document. I don't know why it's under my full-time job, but whatever. And then I have a project.txt file as well. So typically you're only working starting at /home/username. So typically you're starting here. Now on Mac, it's /users, capital U, rather than /home. Now, what happens if you get lost? You can't point and click and double click your way out of a problem. So you have to use commands. The first one is print working directory. I've also heard it said present working directory. This tells you, it gives you the absolute path where you are in the file system. So you don't know, just do pwd and it will tell you. Then you have ls, which stands for list structure. That's going to tell you all of the directories and files that are in the current directory where you currently are. And then you could change directories using cd, which stands for change directory. If you get stuck, just do cd or cd twiddle, and that takes you back to your home directory. Once you're home, home sweet home, there's no place like home. Use these liberally when you do not know where you are in the system and to get back to where you're supposed to be. So I think this is what your example looks like here, except instead of Ryan, it's Ubuntu. So the zip file is all of this down here. So we have school, work, and photos. Under school, we have terms. Under terms, we have classes. Under work, we have organizations. And under photos, we have years for different photos. So we'll do some examples of that. I'll go through some syntax here. The first thing that we're going to do is we're going to start at the school directory in the home file system, the home directory. We're going to use an absolute path for that though. So we're going to do, these are different examples that I have here. Ugh. Maybe not. CD. Oh, I don't have a lamp. Shoot. This is so inconvenient, not having power. Okay, we'll make do to read my notes. So we'll do CD/home /Ubuntu /school. Okay, now I am in, and you can see because it prints it at the command prompt. I am in home school. Little pun there. Then I want to go into, let's say I want to go into the CS143 directory. So let's just go through these examples I have here, and then I'll go through what I have in my notes. Let's say I want to go to the CS143 directory. I can use, again, the absolute path if I know it. So 25W / CS143. And now I'm in that directory. Mind-blowing. So that's the absolute path. Now, if I go back up to the school directory, let's use this twiddle here. Me not being able to see here is going to be really challenging. So we're in school now, and I could do this in multiple commands because typically I'm not going to remember this path. So I'm going to go into, I know I want winter 2025. So I CD into that. Now I'm in the 25 winter directory. I could also use / as well. Now, if I'm looking for CS143, I just now CD into CS143 from there. But there's other ways that I could do this. Let's go back to the home directory in school. I don't have to go level by level in the tree here. I could go automatically to the CS143 directory. I use MSBA 405 in the slides, but it's the same thing. I know that I'm going to find that under Winter 2025, but I don't actually want to CD into that directory. I want to CD into the CS143 directory here. Let's stick with the slide. So MSBA 405. I can skip from my current location to the grandchild location. So 2 levels deeper into the tree in one command, like that. That is a relative path. That is a relative path. Now, how do I go the opposite direction? How do I go up? Well, if I don't want to be in 405 anymore, I want to switch gears to my 143 class. I just do CD .. This takes me to the parent directory. Sometimes you'll also see people put a /. They both do the same thing here. That takes me up to 25W. Now, if I want, I can also skip up 2 levels as well. So to the grandparent. By the way, if you're not familiar with what I'm talking about with grandparent and parent, I'm analogizing the file system tree to a family tree. It's easier to talk about it that way. So if I want to go to the grandparent, which is going to be from here, it's going to be school is the parent, the home directory is the grandparent. So I do CD .. /.. and maybe another / if I want. And that takes me back up to the home directory. Now, to be consistent here with the slides, I'm going to go into the school directory again. Okay, now I can move up and to the right. So I'm in the school directory, and now I want to be in the work directory. The work directory is a sibling to the school directory. So I go up to the parent, and then I go back down to their child. So I can do that like this. I go up a level to the parent, and then I go down to another child. So work. And now I'm in the work directory. Now, if I go back, so where was I before? I was in the home or the school directory. Now we'll do this in one motion here. So we'll go back to the home directory, the school, and now we're going to go into a particular org. So I'm in the school directory now. Now I want to go into the work directory, but for the cloud organization. So that is, oh gosh, so parent. So I'm in school. Parent is the home directory. Work is a child directory, so it's a sibling. So work is a sibling to school, and then cloud is its child. So it's my nephew or niece directory. So I go up a level, up to my home directory. I go into work, and then I go into the cloud directory. I've now traversed to a niece or nephew directory. Now, previously I was in school. Now, if I'm here and I want to go back to the previous directory that I was in, not a level up per se, but to the previous directory that I was in. I actually just learned this. This is new for me. You can do CD hyphen. That will take me back. I was in school, then I went to work cloud. It's not going to take me up to work. It's going to take me to the previous directory that I was in, which was school, and it prints it out here as well. So if you ever, enter an absolute path or some relative path, and you're like, no, I really don't want to be here. I want to go back to where I just was. Do CD hyphen. That's really, really useful. There's another one that you're probably not going to use, at least not in this class, and that is CD slash. This takes you to the root of the file system. So if I do an ls there, I get back a bunch of stuff I don't need. Bin, dev, etc, home, media, mount. Sometimes mount is useful. So you put in a USB drive, it sometimes gets mounted into /MNT, but typically you don't work at the root level. Help, I'm stuck now. I just go back to the home directory with CD or CD twiddle, and there I am. Okay, and if I get stuck, so let's, okay, so I basically did this example already. Let's go back to school, 25W, MSBA. Oh no, I don't know what directory I'm in. Well, it says right here, but let's say I don't have that in my shell. It's not set up that way. If I just type in W or PWD, it gives me the absolute path to the current directory that I'm in. PWD, LS, CD are your friends. You'll use them a lot. Okay. And if there's any questions, feel free to type them into the chat, or I can unmute you, or you can unmute yourself if you raise your hand, and I can help you that way. Okay. Next. I love that transition. So we've talked about CD. You can do everything in one command or in multiple commands. So as I just showed you. So we did this example already, and this example. So let's do an exercise now, which we basically just did. We are, so starting in the home directory, move to the MSBA 405 directory. Let's do it in absolute. So meaning we're not going to use relative at all. We're going to get there in one fell swoop. So let's do that. We're going to go back to our home directory, just so we start fresh. And we're going to go to the MSBA 405 directory. I know, start with what I know. I know I should be in home/Ubuntu. Then I know I should be in the school directory. Oh, by the way, the shell has autocomplete. So if you're lazy like I am, just type SC, and as long as I don't have any directories that start with SC, just hit enter and it fills it in for you. Then I'm going to go into W25W and then MSBA 405. Now I only have one. Whoops. This is getting difficult. No lights. There we go. In one fell swoop, I am in that directory. So I'll write in the slides, CD, home, Ubuntu, school, 25W, MSBA 405. Okay. So we do it. We do whatever we want to do there. Now let's go back to the home directory and do the second exercise. We're going to do this in one command, but relative. So I no longer need home Ubuntu, and I'm also not going to use the twiddle because I'm already at the twiddle, the home directory. So I'm going to do CD. The first directory that I'm going to look into is school. Then 25W, then MSBA 405, relative. So I'll write that out here. MSBA 405. Or I could do this in multiple commands. If you don't know where you are, or you don't know, you haven't, you're not familiar enough with your file structure yet. I try to keep a consistent file structure on my slides and everything so that I don't have to do this stuff constantly. Now, multiple commands. I know I need to go into school. So cd school. Next, okay, do ls. I don't know what's in there. I have two terms, go into 25W. Great, I don't know what's in here. I don't know what I'm teaching basically. So ls, great, I have MSBA 405. I can then get into that directory easily. Now, I want to show you something else that's a little, it's relevant, but a little off the beaten path here. I can also do this, cd school, and I can combine all of these commands into one line by using the semicolon. Now, it's stupid to do this for cd, but there are other commands where you might want to do this. And all it does is it executes each command in line. Now, I'll talk about a couple other things in a moment. So we do cd school, then we're going to do cd 25w. So you see why this is weird now, because I'm losing the hierarchy here, or I'm losing where I am. And then cd msba 405. I cannot use autocomplete here. It still does the same thing, but I can't use autocomplete because I was in the home directory. Now, what does these semicolons do? So I'll type this in the notes here. cd school semicolon cd 25w semicolon cd msba 405. If the first command fails, the shell is going to try to execute the second and third command. And if the second command fails, it's going to try to execute the third command. It's possible that none of these pass, none of these succeed. If the second command is related to the first command somehow, you're going to get a bunch of error messages if the first command fails. So it should just stop. So if the first command fails, it should just stop and not execute the second command. If I want that behavior, I would do cd school ampersand, so and cd 25w ampersand cd msba 405. This is typically used, let's go back here for a moment. This is typically used in shell scripts. Every command in the shell returns an exit code. If a command executes successfully, the exit code is 0. If it doesn't, it's something else. It's 1, -1, 255, whatever. It's just not 0. So with the ampersand case here, if the first command fails, so the exit code is not 0, the command stops. We don't try to execute the second and third command. It just stops. Whereas with the semicolon, we do try to execute the second and third command, which doesn't make sense. The directories don't exist. You could also use pipes or the OR. So cd school or cd 25w or cd msba 405. This is syntactically valid, but it doesn't do what you think it does. If cd school succeeds, we're done. All I do is go into the school directory and do nothing else. If it fails, though, we're then going to try to cd into 25w, which is going to fail because cd 25w or 25w is under school. So the pipes here make absolutely no sense. But sometimes in a shell script, you want to do one or the other, or one of three. And that's what the pipes are good for. Okay. Excellent question. Yes, and you have an answer here. The dot slash is optional. There are some cases where it's not, particularly when executing a command. We'll do that later. Not in this lecture, but later. Okay, so we have our slides. What are we gonna do now? Now we're gonna look at the ls command. We did this already a little bit. ls stands for list structure. But what I want to show you here is that there's various options that you can add to ls to do various different things. So let's go into the school directory, right? Yes, school directory. So we're going to go back into the school directory. So this time I'm just going to use dot dots. I'm in school, cool. Too cool for school. And now I'm going to execute a couple of ls commands. If I execute just ls, I get this. The blue, it depends on your shell. Here, the bluish purple means directory. The white means file. There's other colors that represent different things depending on the shell. What do I do now? Well, I want to know what -L does. What's different here? Just type it in the chat quickly. Otherwise, in 5 seconds, I will give you the answer. So you see a variety. So you may not know all of these columns, and so this is kind of a test. There's a variety of columns here. We have the name, we have the modification date, we have the size in bytes. So these two files are empty, so they have 0 bytes. These two directories, though, this 4096 does not mean the contents of this directory is 4096 bytes. It means the entry in the directory is 4096 bytes. So just the fact that this directory exists takes up 4096 bytes in the directory structure. These two guys, the first one is the owner of the file, Ubuntu. On my server, it would be Ryan. The second is the group that owns the file. So you always have a group that's named after the user. So Ubuntu, Ubuntu. It's possible, though, that Ubuntu could be part of another group. So for example, you as students, if I was a student, I have Ryan, I'm in the Ryan group. I'm also in the student group as well. And depending on which group, what the permissions are, I may own the file outright, or somebody in the group may also have access to the file. And that's what this shows here. This is a bitmask that shows the permissions for the files. And we'll get to that if we need to later. R is read, who can read the file. W is who can write the file. X is who can execute the file like a command. And D is who can view I believe, the directory. It's very bad if the root doesn't have access to D. They can't see anything. So this means this is UGO, so user permissions. I can read, write, execute. Group permissions, so the Ubuntu group can read, write, execute. And others. Others on the server can read and execute, but cannot write, if I have that right. That's what that means. Seems insecure, so I'll double check it. But that's basically how we would read this, UGO. I don't remember what this is. But we'll come back to that. So what does this do? It gives you a lot of details about the directory. So detailed view. Permissions. User, owner, group, modification date, size in bytes, and the file name, file or directory name. What about this little guy here? ls-lahrt. Now, how on earth do you remember these? Well, just from years of doing it. I always use this one. Now, you could actually program an alias so that when you type ls, it actually does this, ls-lahrt. So let's see what it actually does. This is so much better with the big screen. So this is what it looks like. It looks similar. Things are in a different order. What are they ordered by? Look at the times. They seem to be ordered by time. So we already know what L does. What does T do? T orders by time in ascending order by timestamp. The R reverses the order. So now the file on top is the oldest, the file on the bottom is newest. I just look at the bottom file and I know that that's the newest file. What does A do? Some files in Linux are secure and you cannot see them when you do ls. They have a dot before them. So dot secret. For example, Git, when you check out a clone of Git repository in Linux, you get a directory called .git. You should not be able to open that directory. You may have to, but the average user should not be able to see it. Okay. Where was I going with that? Here you have two basically secret directories, the current directory and the parent directory. It's a little weird, but I'll show you a better example in a moment. So that's what A does. What does H do? H shows the disk space in terms of humans. So 4 kilobytes, not 4,096 bytes. So megabytes is M, gigabytes is G, terabytes is T. Now, let me show you maybe a better example. Let's go into the home directory and do another halter, H-A-L-R-T or H-A-L-T-R. You see that I have a bunch of files here. I have profile, bash rc, and bash logout. These are all shell configuration files. I also have an SSH that I should not touch. It contains keys and stuff so that I can log in without a password. I have a cache. I don't know what that is. I don't know what some of these other ones are, but I also have a bash history file. This stores all of my commands since the login. So if I need it, I can get access to it, but I should not see in ls. So what does LAHRT do? Orders by modification time. Descending. Human sizes. All files, including secret dot files. And what else? Oh, detailed, of course. And that's it, right? LAHRT. Yes. Now, that's a good question. So this isn't long format or wide format. I do wonder, though, if there's an analog for that here. Anyway. What do these find commands do? So all we're doing is we're building up. We're combining what we did earlier. So if I want to know, so where am I? Okay, I need to go into school in order to execute this command. And if I want to know what's in the CS143 directory without cding into it, I do this. And that's it. I can put the slash or not. And I see that I have two files, homework1.sql and report.pdf. Now I'm in the school directory. If I want to see what's in the parent directory without going to it, and if for some reason I want a bunch of info about it, I just do LSHALRT // The order of the options doesn't matter in this case. And I see that it's sorted by modification time. So sometimes you memorize these options by like words. So this would be like halter. There's another one that looks like antler, ANTLR. I don't remember what that does, but it's another one I use a lot. Now, so that's that. Okay. What was I going to just talk about off the cuff here? Oh, right. So I may be getting ahead of myself here, but if I don't remember what these options are, how do I figure out what they are? Almost every command has a manual.
Professor, I'm sorry to
Yes.
interrupt, but you're sharing your PowerPoint. I
Okay.
think
You didn't
took
miss
you.
much. Yeah, you didn't miss much. So now we type man, which stands for manual page. I do man and then the command. Now most commands have manual pages, but not all of them do. You'll get an error if you try it without that. So I type in man ls, and it gives me a nice little handbook page about what this command does and the various options. So I see I have -a. It's going to show me all entries. Do not ignore dot files. I have H, human readable. And you see here that I have a -H, which is a shorthand. I always use that, and a longer form. That's maybe more readable, no pun intended. But I don't know a whole lot of people that use that. Now I can page through using the arrow keys, or I can go a page at a time with a space bar. So let's do that. So I've done H, I've done A. Whoops. I have L. Use a long listing format. So there's a difference between lower and uppercase L. I have R for reverse order, whatever I'm sorting by. And I have T, sort by time. Now, once I'm done, if I go to the end of this entry, you see I'm stuck. I keep hitting the space bar and I'm stuck. I just hit Q to get out of it. Another thing I want to show you is, let's say I start typing in this. So just some complete BS. It doesn't exist. Happens all the time due to errors and whatnot. There's a couple of shortcuts I want to show you here. First, I can bail out of this command without having to use the backspace. I just do Command C. Command C will usually set you free. The same thing, if you run a command and decide you don't want to run the command, you just hit Control C and it'll exit out of the command. It's not always perfect. Sometimes it will wait. Sometimes it can still be destructive if it has a side effect, but it's helpful. Now, there's a couple other things that you could do here. Let's say I'm here, I write the clear command, and I want to add something before the clear command. I could use the arrow keys and then type in the command, or I could do Control A and it takes me back to the beginning of the command. I use it all the time. Now I want to get to the end of the command. I do Control E. It takes me to the end of the command. So that's really cool. Now, man pages are not the only way to get help in Linux, in the shell. I should say the shell. Some commands also have help pages or what's called a usage summary. So if I do ls --help, it prints out something similar to the man pages, but it only shows me the options. It shows me what options are required, which are optional, and which I can set for myself, and how to use them. Usage, ls, some kind of option. There may be multiple, that's what the ... means. And then I give it a file or a directory. Now, not all commands do that. Sometimes it'll be -h. It doesn't work here. It does something else. That's going to be human formatted sizes, which only works with L as well. So it really depends on the command. You just have to try a couple in order to figure out what the correct help command is. So that's man and that's help. And that was actually the next slide. Damn, I'm good. so if you want to know what the various options are, it's here as well. So what does LSHALRT do? Well, I just went through a long explanation of that. Okay, so what is next? This is all backwards. That was quite messy. Okay, right. So that was quite messy. You see, I have all the stuff up here that I don't want. It's overstimulating to me. I can't focus when I have all of this text on the screen. So how do I get rid of it? Type clear. Clear is your friend. It takes the command prompt back to the top. I feel nice, fresh, and clean now, and I can type whatever I want now to continue. Now, let's say I write a really complicated command and I don't remember it. It's going to happen all the time. As long as I'm in the same shell session, I can usually find that command by using the history. Remember, I had a .bash history file. This command reads it. So if I hit enter, it's going to show me my history for this shell session. Now, if I have multiple shell sessions open, like I've SSH'd in multiple times, each one's going to have a different history, I believe. And every time you log out, it may be cleared. It eludes me when it's cleared, but it does get cleared. Now, you see that everything just came out all at once, which isn't particularly helpful. I can add, we'll talk about what the pipe does later, so just bear with me here. I can add the command more in order to show me one page of history at a time. And I use the spacebar or the arrow keys to go through the file. There's another command called less, to be honest. I don't know the difference. I should. They've always worked the same to me. I think this little prompt down here is different for whatever reason. Great, so we're done with that. Use Q to get out of it. Now, let's say I find my command. Let's say so this is from last lecture. It's this one. It's 76. I want to write this nasty command.
Professor, I'm sorry. Yeah, I'm sorry to interrupt you again.
All right.
You're not sharing.
So I did history. So really quickly again, here's the history. Here's how you page through the history using the spacebar or the arrow keys to get out of it. You hit Q. More just gives you the same thing. And exit out of it with Q. You can still use the arrows. What else was I going to say now? I can, once I find my long command, which is here, 76, I can use the bash. Oh God, I can't see. There we go. 76. And I'm not going to execute that because it'll take forever, but this will execute that command without me having to copy it or type it out again. So that's pretty useful. Now, one other thing I forgot to mention last time, I'll mention it now. You can page through your history using the up and down arrows as well, if they're nearby. Okay. Okay, some more commands. You can make a directory with mkdir. You can create an empty file without actually having to use a program to do it by using touch. We just lightly touch the file and it creates an empty file for us. If the file doesn't exist, it creates it. If it already exists, it doesn't do anything. It just updates the modification date. We have CP to copy files or directories. We have move, which does two things. It allows us to move a file from one directory to another, or rename a file in the current directory, or move and rename a file into another directory. Then we have RM, which stands for remove. It deletes a file or a directory, and you should use it with a lot of caution because there is no trash can in the shell.
So touch creates an empty text file or just a file that's
It
anonymous?
creates an empty file depending on, um,
The extension.
yes, exactly. Second line is the hard link count. You must be referring to the ls-l, I think, or lahrt. Okay. So where are we now? I think now we do an exercise. Let's see. Let's look at the next slide and see. Yeah, so here's what we're going to do. Perform the following steps. In your little file system that I gave you, your zip file that you've unzipped, you're going to create a new directory under school called 25s cs144. You're going to do this in one command. One command. You're not going to CD, you're not going to create 25s, CD into it, and then create cs144. You're going to do it in one command. Then you're going to create a new file called homework.txt in 25s. You're not going to do number 3. You're going to copy the README file that's in school, I think, into the cs144 directory. You're going to rename the file so that it's now a markdown file. It's readme.md. And then we're going to give it up. We're just going to delete the entire 25s directory that we just created. So let's go through that. Okay, that's clear. And I feel like a hacker here, like writing commands in the dark here. What are some things that we're going to need to do? So let's start in school. Oh, I'm already there. All right, so cool. That worked as expected. There's a couple though. Let's try this. So we're in school. We're going to create a new directory called 25s cs144. So we use mkdir 25s cs144. Looks good. Error. It's a weird error. No such file or directory. The issue here is that 25s doesn't exist. So I can't create cs144. Or can I? Let's look at the man page for mkdir. There's not that many arguments here. I have M, P, V, and Z. V is verbose, don't care. Z is for security, don't care. I don't care about the file mode. The only one that's left is -P. What does that do? No error if the directory already exists, but we create the parent directories as needed if they don't exist. That sounds like what we want. So up arrow to get back to our previous command. And I do a -P, if I could see, -P. And even though 25s doesn't exist, it creates it. And then it also creates cs144 under it. Next. So to do that, we had to look up man mkdir. Now we're going to create a file, a homework file, .txt in the 25s directory. So I'm not going to change directories here. I'm going to stay in school. You should always stay in school. So touch 25s/homework. It would be nice if I could see homework.txt. And now we see if I do ls of 25w 25s, I see I have homework.txt, and I have a CS144 file. So we've done this, and we've done this. Now we're going to rename, oh, we haven't done that. Now we're going to copy the README file into the CS144 directory. So where is the README file? Let's do an ls. There's the README file. I'm going to copy it, not move it. So I use CP. I'm going to copy README, and I'm going to copy into the CS144 directory without moving into it. So 25s slash CS144. There it is. So now if I do an ls on that directory again, I now have a README file in there, and now I'm going to rename it. To do that, I use move. Again, I'm staying here. I'm not going to move, no pun intended, to that directory. So I'm going to move 25s CS144 README to 25s CS144 README.md. Now, this is important because I'm using a relative path. I cannot just list, I cannot just list readme.md. What that's going to do is it's going to move the README file back into the current directory and rename it to readme.md. So now it's moved, or renamed, I should say. And let's test that. I have readme.md. It's a markdown file. And now I'm going to delete the entire directory. So undo everything we just did. So I'm going to do rm 25s, right? Let's try it. Doesn't work. 25s is a directory. It's trying to prevent you from deleting a lot of files. So what do? I don't know. I do man rm. rmdei also works. It's dir. It's the same syntax. I have f force. Okay. Ignore non-existent files and arguments. That might be good. I could prompt forever removal. I won't. I don't care about prompting here at all. And then I have this recursive, lowercase or uppercase r. This is going to remove all files in that directory, the directory itself, and all directories that are within that directory. So it's recursive. So that sounds about right. This is one you should memorize. rm-fr 25s. Now, I no longer have a 25s directory. Now, you have to be very, very careful with rm-fr. It is possible to wipe out the entire system with this command. I'm not going to explain how to do it because somebody might try it. So just be very, very careful. I've done it, and I had to reinstall an operating system because of it. So that's our little example here. And now we can move on. So here, we had to do a man rm or a man remove directory. Now, printing things to the screen or elsewhere. There are two commands to do this. One is called cat, which stands for concat. Meow. We concatenate one or more files together. This is not the best name. Concat also prints a file to the screen. So let's actually look at an example of that. Let's go back up to the root directory or the home directory. Let's go into this PEMS directory that contains a lot of data in it. And let's just see what's in the PEMS stations file. It's a small file, so we're not going to exhaust anything. And cat just prints out the entire file to the screen. Now, I can use cat on multiple files to concatenate those files together. If I do that, it will print out the concatenation of all those files. Typically, though, we don't do that. We typically want to redirect that output to a file, and I'll show that in a moment. Now, there's a second command called echo. Echo. Anyway, that lets you print to a file or print to the screen, one particular string. So cat files, echo strings. So one thing that we commonly echo to the screen is the path, the value of the path variable. So this is where where the shell is going to look for executables. So it prints that to the screen. I can also print stuff to files, and this is very common in shell scripts. You don't want to program something that said go into VI, add this line, and then exit VI, save and exit VI. Instead, we just echo the command into the file. So we'll do an example of that in a moment. We'll come back to this, in other words. Now, as I mentioned, we typically don't want to just print this stuff to the screen. We want to print it to a file. And to do that, we use redirection and streams. So if we want to send the output of a command to a file, we use the right-hand arrow, single arrow. This is a right arrow, no pun intended, W-R-I-T-E and R-I-G-H-T. If the file already exists and I try to write it using this, it will overwrite the file. I've gotten screwed by this many, many times. It's safer to use the double brace, the double arrow. This appends the output to the file. If the file doesn't exist, it creates the file. So there's no harm usually in just appending to the file, unless you really do want to overwrite. You can also read from a file into a command using standard in. So both of these write to standard out, which is just output, and this reads from standard in. Okay, then what? These are called the standard streams. Standard out is the most common stream, and it simply sends all output from a program to the screen by default. There is a second stream called standard error. This is different. It doesn't print out a bunch of informational messages. It only prints out error messages from a program. Two different streams. Maybe we want to process them differently. And then standard in is used when you want to read an entry from the command line or a file. Why do we need both standard out and standard error? It's interesting. One, standard out is very verbose. It prints out a lot of stuff. If you've ever worked with Hadoop or Spark, you know what I'm talking about. It's very hard to track down error messages. There are tools to do it, but it's not pleasant. Errors should be rare, so we don't want to have to sift through this long file. Number two, we may want to handle standard output, so STD out, so just standard, well, typical output, differently from errors. And this is exactly true. You run a web server, you're going to have a log that contains all the transactions on that website by God knows who. And then we're going to have a separate file that contains all the errors on the web server. So errors.log and maybe access.log or output.log. And you as a data scientist are going to want to use these streams differently. You might want to sift the output for certain reasons. In other cases, you may want to sift standard error to look at patterns of when errors occur. So it's very important to have both, but we don't have to. We could just output everything to standard out or to standard error. So let's do a little example here. Oh, let's not. I'm confused by the order here that I printed these in. We can redirect different streams to different places. Let's say I want to redirect standard error so that the errors do not print to the screen and instead print to a file. To do that, I use two right arrow. Standard error is called the second file descriptor. That's what the two means. But standard out will still be printed to the screen. If I want to redirect standard error and append it to a file, well, I do two double arrow file. Again, standard out is going to be printed to the screen. If I want to redirect both standard out and standard error to the same file, I use ampersand right arrow. Or to append, similarly. Now, there are times when I want to redirect standard out to one file and standard error to another file. This is very common. And I do that like this. Right arrow output.log to right arrow error.log. And to be frank, I probably want to do a double arrow here to append of a log rather than overwrite it. Now, there's one case we didn't talk about here. What if I want to shut off standard out or standard error entirely? To do that, I redirect the stream to dev null. Dev null is a little bit of a nerd culture. It just means a black hole. It's nothing. It's the trash can, the round file. So if I redirect the output to dev null, I don't get any output, not to the screen, not to the file. I probably don't want to do this with standard error, but there are cases where we want to do this with standard out. Now, another little joke here I didn't catch earlier. This has multiple meanings. Now we have standard error in statistics and on the command line. Ha ha. Okay. Our next set of exercises. In your home directory, create a file called helloworld.txt with the contents string hello, capitalized, comma, space, world, capitalized, exclamation point. Let's do that. So let's clear our output here. And what command am I going to use to do this? I want to write a string to a file. The file doesn't already exist. I could use right arrow or double right arrow. It doesn't matter. To hello world.txt. What command do I use here? Anyone?
Is it touch?
Echo. So we use echo. We could touch the file and then write to it, but echo will take care of that for us. It'll create the file if it doesn't exist. So echo hello world arrow. Do I already have an arrow? No, I don't. And let's see what we get. Actually, I want to do this up a level, not here. So I could, you know what? Let's do this. Let's use our foo to do that. We'll be lazy. Now I'll go up a directory and I'll cat what's in hello world. And I have that. Now let's do it again. Except this time I have to get rid of the dots. What happens? I should have two hello worlds. Well, no, I shouldn't, because I overwrote the file. So if I want two hello worlds, let's say I want hello brave new world, I should use two arrows. So now if I cat hello world, I get hello world and hello brave new world. So going back to the slides, I do echo hello world to hello world.txt. Now, given a file called exam.sql or SQL that contains a bunch of SQL queries that create a database, like for the exam, I had a long SQL file that created schemas, it created the database, it changed the permissions, it inserted data, all in one file. How do I get this into my SQL? We're not going to run the command. Well, I know I'm going to run MySQL, and I know I have exam.sql SQL. What do I do with it? While I'm waiting, I forgot to mention, even though I'm getting a roster, I would also like to ask you, just in case, please go into the iClicker and do the attendance or however you do that. Mark yourself here. I'll just combine both of them. You know, as long as you weren't here for like 2 or 3 minutes, I'll count it as here. Unless there's a major issue like disasters or whatnot, then I'll reconsider. So this way I have a backup just in case. Yes. So left-hand arrow. We're reading from standard in, just like that. So make sure you do the iClicker. Yeah, so there's a question about the README file. All we did was add the extension .md. Trying to find something creative to do for that exercise. I just checked my email. Goodness. I know there's a lot going on. My other class, I have almost 300 students and people are trying to get in. And the way that it works is that in order to do that, they have to come to a certain number of lectures and sign in, and just to let us know that they're still interested in the class. And we can't do that because it was canceled last week. And now we're on Zoom and they're not enrolled. So I have to somehow figure out how, I guess we have to send an email, and somehow figure out how to get all of those people into the Zoom so that we can count the attendance so that if it'll even let them do it since they're not enrolled. What a nightmare. So I'm getting a lot of emails about that. A lot of you have sent me emails as well about the iClicker attendance issue. I don't know what's going on. Some people are able to do it, some aren't. Um, I have a backup though, which is this Zoom transcript, which seems perfect. I had 130, I think, uh, between now and last hour, the last section. So that's gonna be my master for attendance. And the iClicker will be a backup because I don't know what happened with it. So let's go ahead and get started, unless there's any questions about logistics, and then we will move forward. All right, so we won't get to this topic today, which is regular expressions. I do think it's important, so we'll talk about it next time, and we'll have to change things as needed here. And what we're going to talk about now is basic data management in the shell. So as I mentioned before, we don't always want to load all of our data immediately into R or Python, and we sure as hell don't want to automatically just put it into a database if we're not going to use it past one project. What we can do is we can pre-process our data on the command line or in the shell. Some of you who use Windows and may use PowerShell, you kind of know where I'm going with this. There's a lot of cool stuff you can do to pre-process data before putting it into R and Python, and that's what we're going to talk about now. A lot of the stuff that we talked about in 402 is actually going to come back here. So let's get into it. We're going to go through lots of commands. Now, I am not going to, the way that I'm going to tackle this is we're going to learn the commands as we need them. It's not going to be like in a textbook where all of the similar commands you learn together. And I'm also not going to try not to lecture you on options and commands, but show you how they're used. All right. You had to download from S3 a tarball, what's called the tarball file. Did we talk about that? I'm like, so it's been almost 6. Did we talk about tarball and gzip and oh, you know what? We're going to do that next, I think. I can't remember between these two sections what I've talked about, what I haven't. Anyway, you have a tarball. We'll talk about what that is in a moment. You should have expanded the tarball. You now have a directory in your home directory called PEMS DO7 2024 07. Okay. Now, it, it should be correct. It may be DO7 as well, but it should be 07. Anyway, this data comes from Caltrans, so the California Department of Transportation, which manages all the highways, interstates, federal, state routes, including some major thoroughfares or roads that don't have numbers or aren't part of the highway system and expressways. And it collects a lot of data about them. So every lane has some kind of sensor, a certain distance along the highway that measures the speed and the occupancy of traffic. And it's going to do this, at least the data we're using, it does this every 5 minutes. So it's 5-minute cadence data. And these little stations, there's a variety of them. They're on ramps, they're on off ramps, they're embedded in the highway itself, they're on interchanges, they're everywhere. And they're used to produce the maps that are often used on the news for traffic. I wouldn't be surprised if it's also used for Google Maps and traffic, though they also use Android, the voice device signals for that as well, the density of the signals. So we're going to look at this data. We may do something fun with it at some point. So, just know that. But for now, we're just going to use it to show shell commands. So this system is called PEMS, Performance Measurement System. And it was originally created up at Berkeley. When I first learned about it, it was a Berkeley project. Now it's run by the state. And they measure a lot of data about traffic flow. And we'll talk a little bit about this because it's important about some of the factors at play here. What they do is they measure the weight of the vehicle as it passes over the sensor to predict via a classifier or maybe a rule book the number of axles that are on that vehicle. Why? So that they know how many times to expect that vehicle's wheels will go over that sensor. A motorcycle, very light, should hit the sensor twice quickly. A car, twice, not as quickly. A big rig may hit it 3 or 4 times, if it has, depending on how many axles it has. So we use that to measure how many wheels do I have to wait for to determine that a particular vehicle has exited the sensor, basically. And they measure how long it takes for the entire vehicle to pass over the sensor. And they calculate the traffic speed based on dividing the length of the vehicle by the time it takes to pass over the sensor. And it's measured in feet per second, which is then converted to miles per hour. Now, this one here, and I may have come up with an idea here. This is an oversimplification. How do we measure how long it takes the entire vehicle to pass over the sensor? So I'll continue talking, but go ahead and type in your thoughts here. And there may be an easy way to do it. I don't know. I don't work in transit or transportation. But what you could do is you could look at the weight and you can make an assumption that weight is uniformly distributed across the vehicle. So if the sensor detects 6 tons of force, the back of that vehicle should also have 6 tons of force associated with it as well, because it's the same vehicle. But it may not be true. The front part of a big rig, for example, or what would be a big rig or a truck, may be very heavy. That's where the cab is and the engine and all that. But the back of the truck may be a flatbed, which is much lighter. Are they the same vehicle? We don't really know. I mean, we may know based on the number of axles, and we can count. Well, even though the next two axles were lighter, we know that this is still a triple axle truck. So we know when the end of that vehicle is when it passes over the sensor. But if that's not the case, we cannot make this assumption that weight is uniformly distributed across the vehicle. Then what do we do? How do we identify when a vehicle is completely passed over the sensor? Another thing we could use is we could use time gaps. We hope that a vehicle passes over the sensor start to finish in a uniform rate of speed, rate of movement. Then the next car is going to hit the sensor, the beginning of a sensor, a certain time period later. Now, this time period on a freeway is going to be very short, and it's going to be even worse if the vehicles are stuck in traffic, basically tailgating each other. So, what do we do? I don't quite know because it's not my area, but it's probably a hybrid of the two. Now, come to think of it, what's more important here is the front of the vehicle. There are not a whole lot of vehicles that I know of that are that where the weight is in the back. The entire weight of the vehicle is in the back. Maybe there are that I'm missing, but because of that, we may be able to just estimate the weight from the front, know the number of axles, and just count the number of axles without measuring the vehicle again. That might work. Now, why am I even talking about this? This is called data intuition, and it's very important to develop. I don't know this data, but I can reason through how I might solve this problem. I asked a question like this at Google for the data intuition interviews when I was a data scientist. I asked, how would you measure the number of people currently waiting in the security line of a particular airport terminal? So that we can create the little histogram that shows how busy it is. How do you do that? Do you use historical data? No, I want you to use data that's around you. Maybe cameras, but even better, cell phones, cell phone signals. If you're logged into a Google app, and you opt in to have having that data shared, we can estimate what percentage of people have an Android and opted in and are in the Google app at any given time. Count those people, and then estimate what the total population is that's waiting in line at any given time. So developing this intuition is very important, which is why I wanted to go through it. And I think it's fun. Anyway, I've rambled long enough, and nobody typed in anything for me. Blasphemy. Okay, but data is reported at three different levels. We're only going to focus on the station level. So this is data that's reported by the station, the sensor itself. Now, the spatial level is a little bit higher. It aggregates station data over a particular freeway segment. So maybe I-5 in Burbank, or a route. So I don't know, the spur route that goes from the 105 from the 405 to PCH. That's a little route, or a corridor. A corridor would be something like, we always talk about the Wilshire corridor and Wilshire Boulevard. Same type of thing with freeways. It's aggregated at a higher level. Then finally, we have the geographical level where we aggregate these stations over the city, the county, the Caltrans district, or all of California. So Caltrans divides the state into 12 districts. There's not a whole lot of data, at least not this kind of data, available for districts 1 and 2, which is far northern California. UCLA is in District 7, which contains Los Angeles and Ventura counties. If you're from California, see which district you're from. My home is up here, in Mono County, which is in District 9. So almost the entire drive from LA is in District 9, except for the part in LA or in Ventura County, which is District 7. So you already downloaded the data for all of July for District 7, so only District 7. And it contains data for every 5 minutes. Now, there's multiple ways to get this data onto your computer or onto your EC2 instance. The most popular way is to use the AWS command line interface, which is an API. You type in AWS S3 get or whatever. There's a bunch of different commands you could use here, but there's a lot of problems with it. The authentication is not easy for you, and it's very easy to start getting charged for stuff. So I shared this publicly within the Oregon region. You can just download it via HTTP. That's what wget does. It's like a little web browser, a web client that downloads files from the web pages, files. There's another one called curl that tends to be shipped on more operating systems. It's a little harder to use, but sometimes it's the only one that's pre-installed. All right. The data is hosted in Oregon, just like your EC2 instance. So there are no charges to transfer data from S3 to your EC2 instance. Okay, this is where I talk about tarballs. You've already expanded this file. This is a tarball can be one of two things, but here, what we did is we took all these files, put them into one file, a little library called a tar file or a tape archive. So we don't have a million files. We have one file containing a million files. It's like a directory, basically. Then we compress the directory using gzip. So we took that one little file and made it smaller. And it has a extension of tgz. Tar.tar.gz is the same thing. You'll also see that. Both of these are tarballs. And this should be the V option, not the Z option, verbose. Now, there's all kinds of different compression standards. Typically, tar and another one are used together. So a tarball can either be just a tar file, so one file that contains a bunch of files, or it can be gzipped as well. So here you have the commands to create each of these archives. This is the archive that you, this is the archive you want to create. It starts with archive, and this is what you want to create it from. So a file or a directory. So here, what are some here? We have gzip, very common. bzip2 is a pain. It's very slow, but it compresses, very slow to compress and decompress, but you save a lot of disk space by using bzip2. It can also be combined with tar as well. xz is another one, another common, it's not too common, but it's another one you could use. Gzip and zip and 7z are, you're familiar with those from Windows and Mac probably. But you can combine xz, gzip, and tar. I'm sorry, xz, bzip, and gzip all with tar. All right. So let's first move into the directory where we downloaded our data. Looks like I do have a weird file name here. You may as well. That's okay. We'll go into there. And we see that there's a bunch of files here. It's easier, though, to work with one file. Unless I'm doing something on MapReduce and distributed, I should only analyze one file. How would I do that? What command would I use to do that?
That. Hmm.
What?
That. You want to see like the
Cat.
output. Yeah.
Yes, meow. Cat. So we would use cat for that, not echo. Echo is used for strings. So we can use cat, but what am I going to do here? I can't go through every single file here. It would take forever and it would be very frustrating. What I could do instead is I can use what's called a wildcard in order to create an easier command here. Okay, here we go. So all of my files, we can make this as strict as we want. So all of our files here start with this. Actually, they start with this. The only difference is the number of the day. Now, the only file here, actually, I need to get rid of, give me 1 second. I need to get rid of these other files so that we can recreate them. So Caltrans, just get rid of that. Well, I'm going to do it here. Instead of removing these 5 files individually, I just use a wildcard. Remove anything that starts with Caltrans and is followed by anything else. So let's do that. Okay. Now we're going to concatenate all of these files. Now I could be very strict and use this. I don't want to use asterisk.csv because I have another file here that's completely different. I don't want to do that. So I could do that, do this, or I'm just going to be lazy and start here, D07. So .csv, in case there's any text files that start with that. There's not, but there could be. And I'm going to output this, redirect standard out, otherwise it prints to the screen, to caltrans.csv. This takes a little while to complete, a few moments. And so what I'm going to end up with is I'm going to end up with a single file that I can analyze, not a million files that I have to write a shell script or somehow iterate through. Okay, let's go back here for just a moment. So what do? We're going to do a cat D07 .csv to caltrans.csv while I wait. Now we can go back. I now see that I have a really large file that contains all of the data in one place, which is nice. That's what we want. Now, what do I do with it? I need to understand the data that I'm working with. So the first thing that I might do is look at what some sample rows look like. And I do that using head and tail. Head and shoulders, knees and tail. I just made that up. If I do head followed by the file name, it's going to print out the first 15 lines in the file. Now this file is there's a lot of columns here, so it looks ugly. But you see I have a few things here. I have a timestamp. I have some kind of ID number. I have the district number. I have the freeway number, the direction of travel. This is the type of sensor it is. Like, is it embedded in the highway? Is it an on-ramp or an off-ramp? And so on and so forth. I actually have a lot of other columns here. You see that many are missing. Every
Mister, you're
lane
not
has
sharing your screen.
its own set of columns. Lane 1 has a set of columns, lane 2 has a set of columns, and so on and so forth. So a lot are missing because some freeways only have 3 lanes, whereas the file wants 6. So I can kind of get a sense for what my file looks like. Now, if this file had a header, I could just do head-1, and it would print out the header that shows me what the different columns refer to. If I want to print out 10 lines instead of 15, I just do this. I specify it after the dash, and so on and so forth. Now, I can also do the same thing at the end of the file. Doesn't make a whole lot of sense, but we can do it. I can show the last 15 lines of the file by using tail, or I can specify, the what I want here. Now, this one's important here. Files are constantly being appended to. If I want to see what's happening with the log file as life is moving on, I can do tail-f, and it will show me how the file is changing. Let me see if I can do that here without causing something to crash here. Let's do tail-f, on var log syslog. So this is the system log on this EC2 instance. Okay, so that's the end of the file. Now, as things happen on the system, it's going to print more. And it doesn't seem to be cooperating here, but it would happen. So it would
Professor,
just
I'm
keep
sorry to
printing.
bother you again, but again, I think the switching between the term again.
Okay, so this would keep updating as more and more data comes into the file. At Facebook, we developed I didn't develop it, but we had a system where all we did was tail-f a bunch of log files so that we can turn them into streams. This system was called Taylor Swift. For Taylor, and it was fast, so it was Swift. So it was Taylor Swift. Now, WC is another command that we use quite often. It counts a variety of things. It counts the number of lines, it counts the number of bytes in a file, and it counts the number of words in a file. We don't really care about number of words here, but we do care about the number of lines in the file. So what might we want to use that for? Well, let's do an example of that. Let's look at WC Caltrans. Well, let's get out of that first. And let's see what it gives us. This takes a while, but it's going to give us 3 outputs. It's going to give us the number of lines in the file. It's going to give us the number of words in the file. That's what WC stands for, word count, and the number of bytes in the file. Now, what is another way that's easier, where I don't have to wait here forever, haha, where I can get the number of bytes in the file or the file size? ls-l. So here we see we have, what is that, 19 million rows, 38,000 words in 2.9 million bytes or something like that. My eyes are a little bad here. Now, the other thing I can do, though, is I can just give it -l. Now, while we're waiting for that, I'll just go back to the slides really fast and show that the easier way to do this, if all I want is the file size, is to use ls.l or ls-lh. And then I can see exactly, I don't have to convert bytes. This is 2.8 gigabytes, though, I know. So you see here, we get the number of lines that are in the file. Okay, I need to get my pencil out here. There we go, 2.8 gigabytes. We're going to come back to that number. So this is what the data looks like. We have a timestamp, a station ID, a district number, which is always 7 in our case, the freeway number without I, US, SR, or CA, the direction of travel, north, south, east, or west, the lane type, the sensor type, the station length, which is the amount of length of freeway that station covers, as well as various measures of traffic flow, which we won't worry about for this lecture. Now, based on what I just said, in terms of the pivot, what format is this? Is this long or is this wide? Is this long or is this wide? So I have a set of columns for each lane. Is it long? My silence is suggesting otherwise. So we have a bunch of metadata about the sensor itself, and then we have groups of columns, one group for each lane. In the long format, that would not be the case. In the long format, I would have a row that contained a lane identifier and contained the particular metric that we're counting, so the traffic flow. That would be long format. This is majorly wide format. Okay. So another cool thing that we could do is we can extract columns from the file using cut. So anytime I use these, this is confusing, I know, because these are also used to redirect input and output. Here in this type of example, this is where you put your option. So we can extract columns from a file using cut. So first, we specify the delimiter, then we specify the number of columns that we want, followed by the file name. Now, given what I just said, what is the closest relational algebra operator to cut? Is it the select operator? We're extracting columns out of files.
The projection.
It's the projection, or it's closest to the projection. Okay. So how do we specify the delimiter? Usually with the CSV, we just specify it with the comma. So like this. With a pipe, the pipe is a special character. So we have to put it in quotes like that. Same thing with the space so that it knows what we're doing here. And this didn't come out right in the typesetting. A tab is special. Anything with a backslash is special. So I'd have to do this. Tab delimited files are very common. Now, how do I specify the fields? I can specify them individually, 1, 2, 3, 4, 5, or I can specify a range, 1 through 5, or I can do both. Columns, I want columns 1 and 2, and then columns 3 through 5. Lots of different ways to do it, which is fun. What is the primary key of this data? Why does the chat's like weird. It like doesn't jump down to the newest message. Station and timestamp, good. I agree. There may be one other, I'm not positive. It may be the freeway number. Why might that be? Meaning it's part of the primary key, not a second primary key. Some of this data involves interchanges. It's not clear to me how the interchanges are coded. So it's possible that the same sensor appears twice, one for each freeway in the interchange. So I don't know. I'm going to say it's timestamp and station though. Plus station ID. All right. Now, this data is not normalized by a long shot. It's in wide format as it is. So we're going to create a new data set that's closer to normalized. It still won't be normalized. It won't be in third normal form or BCNF. Let's write a column that reduces command that reduces the number of columns in this data set. So we're going to create a new data file that does not contain columns 3, 8, 9, 10, 11, or 12, but contains all of the others. Now there are 52 columns in total in this data set. We're going to call the new file Caltrans new. Write the file in the, you don't have to do this if you don't want to. I don't know why I did that. So let's go ahead and do that. And I will explain how this works. So I wish I could expand this, but it might screw up the view. I'm going to specify a comma. I don't want 3, 8, 9, 10, or 11, or 12. So I do want 1, 2, 4 through 7, and 13 through 52. I extract them from caltrans.csv and I write a new file called caltrans new. So let's do that. Now, what we just did, can you think of any problems with this approach? There's a major one. Where all we do is we use cut in order to separate this delimited file into columns. Major problem that you're going to have to deal with over and over and over again. Let's say, so maybe in this particular data, that isn't a problem. Let's take a look. But in general, this is very problematic. Yeah, so in this particular data, it's not a problem. But what if we have text? What if we have any text in this file? Would that be a problem? You could have duplicates. Yeah, that's not so much of a problem though. The problem is that we have embedded commas. Let's say one of the columns is in quotes. Newbury Park, comma, Thousand Oaks. Cut is going to split on this, which is not what we want. The comma is embedded. So the cut is not very smart with text here. Now, if you're using Python, for example, you're going to run into this all the time. Same thing with R. You have to tell it what character you want to use for quotes. Did I lose my audio? Oh, there it is. All right, never mind. Okay, so it's something that you're going to run into all the time here. So this is not a great way to do this, but in our case, it's fine. Now, the paste operator is the opposite. I've only used this once or twice, usually for pedagogical reasons when I'm teaching. But let's say I have data where each column, I have 3 different files. They're all sorted in the same order. One file has 3 columns, another file has 1 column, and all I want to do is stack them next to each other, which is a concat, I believe, in pandas, or a cbind in R. Essentially, is what I'm mimicking. So R concat PD or cbind in R. So what I do here is I'm just taking this file and I'm pulling out 2 columns, and then I'm pasting it back together. I specify the delimiter, the 2 files, and give it a new name. And it's going to paste those 2 columns next to each other, which is pretty cool. Don't worry too much about this command below here. Basically, what this is doing, a diff looks for differences between 2 files. So we don't want any output here. It means there's no differences. This is the file we just created, and this is cutting the original file on columns 1 and 2. So there should be no difference between those 2. So that's all that's doing. I don't think I did an example. It takes too long to run, so I didn't do it. Now, get a grep. So filtering data. Very, very common that we filter data. It's one of the most common ones that you're going to use. You can use grep with strings and values or with regular expressions to try to match regular expressions. Today, we'll just talk about values. So some common options with grep are ignoring cases, only showing the matching part of the line. So you have a pattern, but you only want to extract what matches the pattern. You can do that here. You can also invert the search. So you can find text or records that don't match what you're looking for. So let's do a couple of exercises involving that. Exercise 1, create a new file called Caltrans 405. This is going to come from Caltrans new. That only contains readings from the 405 freeway. Now, if you're astute, you're going to notice a problem here, and we'll talk about that. So let's do that. Let's show what that looks like. So I have my grep command. Then I have the pattern or text that I want to look for. I know that the 405 freeway is going to be represented in a column surrounded by commas as 405. So I'm just going to search the file for that. Seems reasonable. Is there a problem with that, though? Yes, there's a problem with this. There's a major problem with this. The problem is that we're assuming that comma 405 comma can't appear anywhere else in the file. So that's bad. It's not generalizable. And I want to show you how we know that. So we haven't talked about all of these commands yet. But I have this Caltrans 405. This is only supposed to contain sensor readings from the 405 freeway. So what do? I take that file, it's comma separated. I extract the 3rd column, which is the freeway. I don't worry too much about this yet. We haven't talked about it yet. So if you don't follow yet, don't worry about it. What I'm doing, all I'm doing is I'm showing you why this is a problem. We're going to sort on that column that we just got back, the freeways, and we're going to count how many occurrences of each unique freeway appear. This should be 405 only with a high count. Let's see what we actually get though. So this is a way that you can use these commands in order to check your data integrity and sanity check your data. We see that my assumption is violated. Yes, there are a lot of 405 freeways, but sometimes comma 405 comma is used in other situations. For the 2 freeway, the 105, the 60, the 605, and the 91. This is bad. So what would I do instead? Instead, what I'd want to do is I'd want to create a regular expression that matches, and only when column 3 is 405, not just matching 405 anywhere. So we'll talk a little bit more about this in a moment. Now, going back to the exercises, exercise 2. Let's say station 715898 produces faulty data. We don't want to analyze it. Shall we throw out that sensor? And we throw out all of its data. We're not going to write all of the command here, but how would I do this using grep? Again, we're making an assumption that we don't have any other 6-digit numbers. I think that is safe here. How would I use grep to do this? What's back here? Anyone? There's only 3 options here. Okay. So -O only shows the matching part of the line. So if I do, let's try that. Grep O. What was it? I also need to switch to the terminal. I'll do that in a moment. 715898. Caltrans new. Is that right? Yeah. Let's see what we get. That's what we get. -O only matches where the pattern matches or where the value matches, and only returns the match. So if I'm searching for 715898, all I'm going to get back with -O is 715898 for every row that has that value. So is there something else I can use? I. Why I? These are numbers. Are numbers case sensitive? V, yes. So what this is going to do is going to find all lines that do not have 715898 and creates a data set from them. So I think I called this clean or something. So -V inverts the match. So lines that do not match. Okay, grep -V. Put that in there for you. Now, sorting. In a standard programming language, we don't always need, we can sometimes assume that our data fits in RAM. But when data doesn't fit in RAM, we have to make a lot of different optimizations. One of the things that we can do is we can sort the data before we process it. Now, we no longer need to read all the data into RAM and check all the data. All we need to do is kind of walk the files and check for equivalence. So let me give you an example. Let's look at a join. I could, so I have a table here, a table here. I check this value, this value, this value, and this value. Then I move to this one. I check this value, this, and this. And then here, this, and this. I do n squared comparisons. That's called a nested loop join. It's a pretty standard join algorithm. Let's say I sort the data, though. The complexity actually ends up becoming O of n plus n. Or you could just say O of 2n or O of n if you want. Because the data are sorted, all I'm doing is I'm maintaining a pointer on two files and comparing the values and then printing out the values if they match on the join key. That's sometimes called a merge join. It's very efficient, but it requires you to sort the data first. So it's not only just O of n plus n, but you have to pay an upfront cost of O of n log n plus O of m log n, m, like that. So it would end up being, which is O of, I don't know, m log m plus n log n. If you don't worry about this, if you don't follow big O notation. The point is that I'm trying to show you that by sorting the data, you can get a big performance boost and not have to read everything into RAM. So that's why we use the sort command so extensively in this shell. We use it to sort files. We can use it to sort delimited files. We just specified the delimiter of -t. We could, choose to make it case insensitive. We can treat numbers as numbers using -n as opposed to strings. We can reverse sort. We could specify what column we want to do the sort on. We could specify a range of columns. We could specify exactly one column. Or we could specify multiple columns that we use in the event of a tie. So first, we'll sort by column N1. And if there's a tie, so a matching value on N1, then we sort by N2. These all act very differently. And it's very confusing for me as well when I was learning this. We can also simply check if the data is sorted by using sort-c. It doesn't actually sort anything, it just checks if it's sorted. So what does this first one do? -k2, 5. It does not sort by column 2 and then by column 5. It sorts by 2, 3, 4, and 5 composite. So if you want to do a typical sort, you're looking at this one here. Okay, so what bugs can occur if we do not use -n with numbers? So we want 1 to be less than 2 to be, or let me write this a different way. We want 1, arrow 2, arrow 3. What do we get if we don't use -n? We get 1, 10, 100, 1,000, 10,000, so on and so forth. Then 2, then 20, and so on and so forth. It's sorted in lexicographic order, which is not usually what we want. So what caveat must we be careful about with the -k? Well, I kind of just went through that. It sorts on a composite. It doesn't sort on 2 first, then 5. It's a range. Does not sort by 2, then 5. That needs -k2, -k5. You guys are very quiet tonight. So if you have any questions, please make sure you ask. Okay. Now we're going to move on to something else fun. We have another data file here called PEM stations.
Can I
Here's
ask?
what it
I'm
looks.
so sorry. Can I
Mhm.
ask a question about the sorting?
Yeah.
So the sorting, you said you have a file and you can select which column you want to sort by, and that's the
Mhm.
number 2. And if you put like 2 times 5, 2 comma 5, it treats the whole thing as one entity and then sorts by
Yeah.
that.
Yeah. It treats columns 2, 3, 4, and 5 as one thing to sort by.
And how do we make it? And the slash k sorts 1, then 10, then 100, then 2, or is it the slash n? That's the part
So
I don't.
that's a different problem. That's a -n. If we want to sort numbers, we have to use -n if we care about the numerical value. That's going to give us, 1, 2, 3, 4 sort order. Whereas if we don't, it's going to be treated as a string, and we get 1, 10, 100,000, blah, 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 then 2,
So if we
20.
use dash K for numbers, we get the 1, 10, 100 this. Am I
Dash
correct?
K is used to sort certain columns.
Columns also, okay, sorry.
You're picking a column to sort by. Dash N just says to treat numbers as numbers.
Okay.
So this is what we have another little data set to work with here that contains metadata about each station. So let's take a look at that. Oh, or we're not going to do that yet. Okay, so what we're going to do now is we're going to sort the original Caltrans file by the station ID, which is the second column. And we're going to create a new file called Caltrans sorted. Now, the reason we need to do this because of something that we're going to do downstream here. So we specify our delimiter is a comma. We're going to sort first by the station ID and then by the timestamp. Treat numbers as numbers. All of this data comes from Caltrans new, and we're going to store the sorted order into Caltrans sorted.csv. So I'm not doing this just to do it, to show sorting. It's because we need to do this. So I'll write this out on the slide. Sort blah K2 K1 dash N Caltrans dash new dot CSV arrow Caltrans sorted dot CSV. And this one takes a little while to finish. Now, why am I sorting? I'm sorting because it makes doing a join much more efficient. I can't read all of this data into RAM. So, yes, we're going to do a join again on the command line in the shell. But I have to sort the data first. So I have that PEM station file containing metadata about each station, and I want to join it to the original sensor data. So now I have a fully formed row containing the sensor and all of its information, as well as all of the readings from that sensor. Horribly unnormalized, but at least when I look at the row of data, I have all the data that I need. And so, I'm back here. The PEMS data contains the following information: the station ID, the county ID. We're only going to have 2 county IDs here. We have 37, which is LA. Unfortunately, I can't find the mappings anywhere, but I could tell. And 111 for Ventura. We have city IDs. Again, I couldn't find those. The state postmarker. So this is the number of miles along the highway within the state of California. The absolute postmarker, which is the number of miles regardless of which state the highway originated in. So I-5 starts in Washington, I think. So it's going to contain the mileage from the beginning in Washington. We have the latitude and longitude of each site, which is really cool. So we can create maps and stuff. We have the length of the freeway that is managed by this sensor, the number of lanes that are in that freeway, and the name of the station. So now we have a little bit of text data to work with. To join 2 files together, we just use the join command. Again, you have to specify a delimiter because we need to specify which column contains the join key. We specify the left and right hand side of the join using -1 and -2. We give it the column names where the join key is between the 2 files. If they happen to be the same column number, then we can just use -J. Then finally, if we have a header in both files, --header just tells the processor to ignore the header and not treat it as part of the join. So hopefully this finishes soon so we can do an example of that. So our next exercise here is to join the PEMS metadata with the Caltrans sorted data to create a full data set called Caltrans-full. Now, to save some time here, whoops, we do not need to sort the PEMS metadata. It's already sorted for us by ID number. So that helps. So any day now would be nice. Okay, it's still running. Okay, so let's get my join exercise up here. Meanwhile, are there any questions while we wait for this? Let's see if there's something I can move on to while we wait for this, or go back to. Ay, 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 you're killing me here. It's a big file, 3 gigs, millions of rows. Let's maybe come back to the join. Let's actually go to the next question. So, oh, thank you. All right, so now we can do our join. Same thing here. Can you see that? Yeah. All right. So join command, I specify I want to join on the first file, I'm joining on column 1. And then on the second file, I'm joining on column 2. My delimiter is a comma as always. I'm joining PEM stations, that's file 1, with caltrans sorted, which is file 2. And I'm going to redirect the output to caltrans full. So let's run that. Now, when you're doing joins like this, you want to make sure that you don't violate your data integrity, that you don't gain or lose data in the process. This typically means that your join condition is incorrect or the assumption about your data is incorrect. It could also mean that you have a problem with your data. What's something that I want to check once this join is done to make sure that our data is in good shape?
The maximum number of rows should be equal to first of all, is this an inner join or a left join?
That's the next question. Is it an inner join?
If it's a left join, the maximum number of rows should be equal to if it's a left join, the maximum number of rows should be equal to the maximum of the one on the left, or
So
equal to it.
every sensor has a sensor ID. Every sensor ID should have data associated with that sensor ID. So let's look something up first, because you bring up a good point. If I can see here. I have my join column here, which is J, or 1 and 2. There's something else here that I wanted to see. Now I'm not seeing it. Here. I think that's what I'm referring to here. If I interpret this correctly, it looks like what's going to happen is if I join and I do not have a match, it's going to fill in with a particular string. If I specify -E. So in a database, it would fill in a null, right? If there's no match on the
If,
join key, potentially,
on the left join, yes.
if it's a left join, yes. So to make this more obvious, you cannot, I don't believe you can do an outer join here, at least not a very clean outer join compared to in a database system. So what might this join be then?
Inner.
Inner and
Inner or Cartesian, it's one of them, and I hope it's
inner
not
and
Cartesian.
equa.
Inner and equa, okay.
So in our second question, so basically every sensor ID should match to a sensor ID in the PEMS metadata. It's a one-to-one correspondence. Could be one to many. It would be one to many if one is the metadata. And so, yeah, you're right. It would be the maximum of the two. So we want to make sure that the maximum of the two, if we count the number of lines in the join, it's equal to the maximum of the PEMS metadata and the caltrans full data, right? So what we can do I'll let this run for a little while, and then we'll move on, and then we'll just let this run for a little bit and then come back to it. So what we can check is the word count or the line count in the original data file, which is the bigger of the two files, and in whoops, it's not sorted. No, that was right. Okay, gotta copy that again. No. All right. So we'll run this, and we're going to count the number of lines in the full file and the number of lines in the sorted file. They should be equal to each other. We'll see whether or not that's the case in a moment. But let's move on for just the time being. So we would use WC-L here. So we've learned a lot of commands, and we're kind of stuck now. We can't do a whole lot more basic things with just what we've learned. We have to now combine commands together in order to really be powerful here. And we've seen a few examples of this, but now we'll go into more detail about those examples. Is there a way to combine commands? Yes, there is. There's actually several ways that we can be more powerful with our analysis. We could use regex. We could use awk, AWK. We could use sed, SED, the stream editor. Or we can use pipes. So, of course, now it finishes. So let's go back. Here's our result. We see that they're not equal. We're off by about 35,000 rows, I think, or 300. I counted 35,000 when I did it in R earlier. And the reason for that is that some of these sensors are in the metadata, but not in the sensor data. And some of the sensors are in the full data, but not in the metadata for some reason. They may be new sensors, they may be old decommissioned sensors. And for some reason, they only update this metadata once every few years. So because of that, we end up losing those rows and we do not get a perfect, well, we get an inner join, but we don't get a perfect match as we would expect. We do lose some data here. So are there any questions about using that command to show that? All right, pipes. We could replace everything that we just did with one command using a pipe. A pipe is just this little vertical bar, and what it does is it takes the output of the command that's on the left-hand side and pushes it as the input to the command on the right-hand side. So you can think of it as an arrow like this. It takes the data out to in. So we could write our command like this as follows. We first combine all of the CSV files into one file and output it. Then we took that output, eliminated several columns, took that output, sorted by the station ID first, followed by the timestamp, took that output, and then joined with this file pemstation.csv. Now, this command here is a little bit weird. I'm doing this on purpose. The join command takes two files. It's a join, but we don't have two files available here. We have one file and a stream that came from a pipe, the pipe being everything above the join. So in order to tell the command that we want to read the data from a stream and not from a file is to use the hyphen. That means all of this, the result of all of this is going to be put in here. So we're joining pemstation.csv with all of this. So we can run that command like this. Now, you see some of these backslashes here. Don't be confused by those. The backslashes only mean that this command is one command that is split across multiple rows, multiple lines. If I write this all in one line, I don't need the backslashes. Yeah, so we'll just put it in that file full. And that's the point here is we want to be able to create these workflows so that we can efficiently analyze data without having to create a bunch of intermediate files. They take up space, you lose track of them, they may have data integrity issues. This is a reproducible workflow that you can use. If you've used dplyr in R and with Magritter, you've used pipes extensively. It uses this little, if I remember correctly, I think it looks, whoops, I think it looks like this nomenclature. Julia can also use pipes. SQL can also use pipes now. DuckDB supports piping, pipe SQL. and whatnot. So it's becoming more and more popular, but it all originated here in the shell. So to show you the slides here, what I wrote, we're going to shove all of this into here. And this is what you get from dplyr, basically. That's the way you form a pipe in R. So if there are any questions about the hyphen tripped people up last section. Okay,
Looks similar to R, right?
it
So
does.
and we did in R, you could pipe the output into the next one. So
Yep. Yeah, it all comes from this. Yeah. And it also looks similar to relational algebra in SQL, as we'll see in a moment. Okay, so we covered this. We have one more command to talk about that's important, and that's the unique command. The documentation says that all it does is it dedupes rows, and it does do that, but you can also use it to count the number of you can get it to extract unique values, but you can also count how many times each unique value occurs in a particular data set. But there's a catch. You have to sort the data first in order to use unique. So let's look at an example of that once this finishes up here. So unique -c is very, very common. Let's look at how many stations there are in the data. This is how many station IDs there are in the data. I have many, many duplicates because I have many rows per sensor. I think my instance is running low on RAM, so it's like going really slow. So let me just write it out while this is still executing. How would we do that? Well, we first need to extract. There we go. It's always right when I'm about to give up. The first thing we want to do is we want to extract the ID column, the station ID column, which is the first one in this join data set. Then we're going to sort, because I only have ID now. So I sort ID. I don't need to specify a column. I'm then going to take the unique IDs. So now I have a bunch of unique IDs, and then I count them using the line count. So this should give me like 2,151. So, I forgot to do that again. So here we extract the first column containing the IDs. We sort those IDs. We make them unique, and then we count the number of unique ones that we have. Okay, 2,151. That's low. Most of the sensors are in off ramps and on ramps, which I excluded here. Now, let's output the top 5 city codes in Ventura County. So county is the second column. Ventura County is 111. And we want the top 5 city codes. So meaning they appear the most often. That's going to be in column 3 in the full data. So let's take a look at that. First, I need to filter down to Ventura County data, which has code 111. So again, I have to use this not great way of finding that, comma, 111, comma. And I search through the Caltrans full data. Once I've done that, now I only have Ventura County rows. I extract the city code from that and sort them. Then I count how many times each unique city code occurs. That's going to give me a number. I need to sort by that number in reverse order, most frequent to least frequent, and then take the top 5, the highest 5. So we could do that here. And you'll notice something interesting here as well, in that the city code is not always populated for some reason.
Professor, what if a random line, has the sequence 111? Oh yeah,
Yeah,
it
and
has
that
to have comments in between.
yeah, and that could very well be the case. We haven't talked about regular expressions yet, though, so I have to make an assumption here that that doesn't happen. But it's probably absolutely violated. So I have city. I think the left-hand side is the city. The right is the count. We see that the most common city is whatever this one is. We also see that, oh no, it's the other way around. A lot of records do not have city codes. So city 78582 has the most records, which is probably Los Angeles. Now, what is the point of this? The point of this is to explore the data and see what we have. So let's do one more exercise. We're going to count the frequency of each sensor type. So we know we have these sensor types. We don't know what they are, what the values are, and we don't know how frequent they are. So I'm going to extract column 14, which is a sensor type. I'm going to sort the sensor types and then count each one as a group. Now, while this is running, I'm going to point out that some of these operators in these pipes are commutative. It doesn't matter what order you put them in. Some of them, it's not always the case, but sometimes you can. And then we are almost done. We have 2 more slides. Okay, while that's running, there we go. So ML is an embedded sensor in a freeway. So that's the most common type. I could have sorted again, but I didn't do that. FF is a freeway interchange, freeway to freeway. And CD is a sensor at a collection box. So this would be like a toll box, a toll booth, or a fast track collection monitoring system. So I eliminated a lot of other types because they were so big. This file would have been 100 gigs if I didn't filter. So yeah. All right. So all of this is related. This is all relational data. All of this is related to relational algebra and SQL. Let's take our most gnarly command, which is the one that we did for the cities, and let's write a relational algebra expression for it. Now, let's see. That's this guy here. So grep la caltrans full dot csv slash cut something slash sort slash unique c sort again head 5. All right. What is the relational algebra expression for this? Well, we're going to call our data set R. And the first thing that we did is we filtered. We filtered down to the situation where the county code is 111. So that's this. County equals 111. Next, we cut. We projected. We only extracted certain columns. So we cut, what did we pull out here? What was it? The 3, which is the city. Then we sort. So relational algebra doesn't have a sort. We don't need it. Then we did a unique. And we counted the number of uniques. So what did we do there? We did a group by. The left-hand side is what are we grouping by? We're grouping by city. What are we counting? Distinct count. It's hard to read. On, what was it? Oh, just the number of rows. Distinct count of rows. So that's our relational algebra expression that we just did. How would I write this in SQL? I have from Caltrans, we'll call that the relation, where county equals 111, group by, let me actually fix that. I got into trouble with that last time. So it's select city from Caltrans where county equals 100 in a subquery. Then we do select count C, select count C from group by city. Or just do count 1. That makes more sense to me. Group by city. Whoops. And I think that's what I wrote last time. Let me double check.
It's not count distinct C.
I have count 1 here. So select
But there,
C,
the C will not have duplicates, right? Because it's a view. Anyway, maybe I'm
select
wrong.
city as C from Caltrans where county equals 100. So I'm gonna get a bunch of duplicate city codes back, and I want to count those. So I group by city, and
Okay.
I count one on that. I think that's right, and that's what I have written. Oh, and then what do? I order by C, which or count one. So let's call this count one as CNT. Order by CNT descending. Finally, limit 5. That's head 5. It's almost the same thing between the shell and SQL and relational algebra. It's beautiful. Any questions about that?
Just, I know it's not related to this course, but shouldn't the group by be in the inner query or not? Am I missing something? No.
You may be able to
Maybe.
write it that way, but all I'm doing here is I'm just selecting the city.
Okay.
So selecting
Okay.
a bunch of city codes, and then I group by the city code and count the number of times that city code appears.
Okay.
There may be another way to do it without a subquery, though. So, another data intuition problem. My original data is 2.8 gigabytes because it's measured every 5 minutes. Let's say instead I use data that's measured once an hour. What's the data set size going to be? This is important to know. What would I divide by here?
Instead of an hour, 5 minutes, you divide by 12, right?
Yep, which gives me about, I had already computed it, about 260 megabytes. So we save a lot of data that way. All right. Long 6 hours. Um, so that kind of completes today. The good thing about not getting into regular expressions is it means your homework is going to be fairly short again. So let me just zoom to the last slides here. You should clean up your EC2 instance now. Unfortunately, this got cut off. But what you want to do is you want to delete the TGZ file. You may want to delete all of the original data files. So that started with what was it, D07 something CSV. You might want to delete those and just keep caltrans.csv, the master file. Delete all the other CSVs that we created. We use the pipe basically to recreate those without actually writing them to the disk. So otherwise, you're going to run out of space throughout the quarter. Homework 2 will be released on Wednesday. It's only going to cover Unix commands for navigation, as well as Unix commands for file and data management. I'm going to make this, I'm not going to say tricky, but it's going to require you to read the documentation. So it'll be good research skills for you to learn on your own and not just regurgitate what we did in lecture. So be on the lookout for that, and the TAs will start grading homework 1 very shortly. I'll be around for a little bit until 7 if there's any questions. Otherwise, thank you everybody for. I know it's challenging right now. It's very tiring. Thank you everybody for coming. Thank you for your attention, and I will see you all next Friday at the makeup lecture or office hours, which will be at Zoom this week. Check Piazza for those office hours because I've changed them. So thank you everybody.